So let's talk about biomarkers, and let's put them on land, or take them from land. And so remember my discussion earlier about thinking about the transport processes and the environmental controls on what we actually get. What we are interested in is reconstructing this, and what we get is this. And so we have to understand the controls on the properties of these to try and understand these environments of the past. Lots of other people do this, and they do it very well using pollen, not to scale, and fossil leaves, not to scale, right? But so there's a really, I think there's a lot to be gained by interacting as geochemists with palynologists and paleobotany colleagues, because you learn a lot about how they think about things, and your work is complementary and theirs is complementary. So I want to encourage geochemists to get out of the lab and go talk to paleobotanists. Here's another famous geochemist, Jeff Eglinton, who was starting his career at a really auspicious time. He was a chemistry PhD and was working at a time when gas chromatography first happened. And he was one of the first to say, hey, let's put natural things through these gas chromatographies or chromatographic systems. And let's look at these compounds as they come out and go into a mass spectrometer and figure out what their structures are. It's so amazing. One of the first compound classes that he worked with were the waxes that are on the surfaces of leaves. This is a blown up image of a cabbage leaf, and you can see these are not glass spheres, those are drops of water. And so there's no surface tension there, and it's because it's kind of like a raincoat. It's covered with this waxy layer, and then the water, it balls up on top. And that waxiness, there's a lot of compounds that make that up, but they include long alkanes that don't have any functional groups to them. They're just carbon and hydrogen, and they come in sort of these odd chain lengths, so 23, 5, 27, 29, 31, 33, 35 is hiding down there. And Jeff realized that these long chain odd alkanes are a characteristic of leaf waxes. Excuse me. And he did a lot of work on this, and he really popularized their importance. And they're used to, for example, in petroleum studies to show that there's terrestrial influence in the organic matter that ends up as petroleum. And then more recently, I would say in the last 10 years, they've reemerged as a really important suite of biomarkers because they carry not only carbon, but they carry hydrogen, and they're now widely being used as a proxy to try and reconstruct water isotope distributions on the land surface. If we look at them at another cross-section, so my geology coming through again, this is now cross-section of a leaf from a review article. There's the cell wall, and then there's this cuticle sort of layering, a waxy layer on the outside, and then on the very surface are these crystals, and you can see these crystals. Those are crystals that are comprised of these long chain hydrocarbon compounds. So they're kind of coating the surface of the leaf, and it's really interesting. There's a lot of sort of discussion about what they do, and maybe somebody here knows why, functionally what they do. I thought for a long time they prevented fungal attack until my friend who studies fungi set me straight on the kind of horrible, nasty attack mechanisms that fungi can use to attack a leaf surface. These lipids don't stand a chance. So I remain open to other ideas for what they do. I don't know myself. But they are pretty prominent, and they're characteristic of vegetation. And Jeff showed us that. We got interested in how much, right? Because we're thinking about this flux, right? We're interested in how much is out there, and do some plants have more than others, and why is that? And so some work by my former student and IsoCamp alum, Aaron Diefendorf. I thought I had it. There it is. Shows the concentration of these waxes as a function of different taxonomic groups that he sampled. And these are the N-alkanes per gram of dry weight, so it's a mass-to-mass ratio. It does not scale with surface area, so when we count for surface area of the leaves, it's something different than that. So they're proportionally variable as a function of phylogenetic origin or affiliation. And what's interesting is that these over here are all gymnosperms, and over here these are all angiosperms. And so the angiosperms in our initial work really popped out as having a lot more leaf waxes than the gymnosperms. And so we published this diagram initially and said, hey, those of you using N-alkanes for climate reconstruction, you should know you're not getting the gymnosperms, or at least proportionally you're not getting a lot of them, and it's really the angiosperms that are represented in these compounds. Aaron then went on and published a second paper that really looked in detail at the gymnosperm distribution, and he brought, this is sort of a limited sampling, so he expanded the sampling of it and found, oh yeah, no, there are plant waxes in these taxa, but the scale is different. So this scale bar here is that, right? So they're still lower in abundance than a lot of these other angiosperm species. And so that's a pretty interesting sort of thing, and we don't fully understand all the nuances there, but again, typically in the geologic record, if you're finding N-alkanes, they're probably biased by angiosperm inputs, less so by gymnosperms.